You're listening to The Weather Junkies.
Oh boy. Large wedge tornado coming up into Tuscaloosa. A winter storm warning is in effect for our area.
So we can expect at least another 2 to 4 inches overnight. Then that snow is
The National Weather Service in Huntsville has issued a tornado warning for northwestern Massachusetts.
14 to 22 inches of snow!
Good Thursday evening. Thank you for joining us here on the Weather Junkies. We are very excited for our special guest this evening, one of the nation's leading radar researchers, and we'll have him on later in the show. First, though, we want to go through the weather that we're seeing now and a few tweets. Of course, I'm joined by Dakota Smith live from Colorado. Dakota.
Hey, Tyler, and thanks everyone for joining us tonight. It's another great day in Fort Collins, Colorado. God, the weather out here has been exceptional. We got into the 70s today, partly cloudy skies, and nothing to complain about. I'm assuming the weather isn't as good, but I think it's gotten better out there in the Northeast.
It has. We've had a couple days where it's been sunny, and I think we were in the lower 80s today. I don't know exactly what the high was. I saw at least 81. So much improved since the last time we've talked, and we actually had some smoke overhead today from the Canadian wildfire, so there was a bit of a gray filter to the sky, and tomorrow there'll be a few showers, weekend so-so, but finally the trees have really turned green, and the allergy sufferers have really been suffering. That's not me, but I know a lot of people have been. I know for a fact I've been able to get a few great pictures of the colorful trees and flowers, and a lot of things turning green though now. So the time is almost out to get some great spring photos. It's more like summer now, but that's exciting.
Yeah. I know in DC, they've had 15 days of straight rain.
At least.
Which I believe is the record down there.
Crazy stat.
Yeah, at least you guys didn't stay under that kind of marine cloud deck for that long.
We suffered for like 7 or 8 days, but certainly not nearly as long as DC. I did see a tweet that said it was the longest on record, and that was like 4 or 5 days ago. So
yeah,
I'm sure they obliterated the old record for longest streak of rain in general, probably. I don't think it's limited to May.
Yeah, I think for DC, that's their longest ever. I saw that Seattle holds like the longest with over 30 days of straight rain. So, at least they're not in that situation. But it makes sense, though. I guess Seattle holds that record. We can hop over into our tweets now because, we haven't had that exciting of weather in the Northeast in Colorado. My first tweet tonight is from Steve Hilberg. You can follow him at hbergsteve. He said, "Why do we need CoCoRAHS observations? More observers means better chance of documenting events like this." And it shows a picture of a map with very low rainfall reports, less than an inch, most around a half inch. And then there's one tiny little area, there's upwards of 2.5 to 3 inches, which wouldn't have gotten noticed except by radar. Radar would have noticed it, I assume. But otherwise, it wouldn't have been picked up from the ground. So it shows very interesting, local things that can't be picked up by just our National Weather Service stations and ASOS and AWOS.
Yeah, we absolutely need more observers. CoCoRAHS actually does an annual campaign to recruit volunteers. They call it CoCoRAHS March Madness, so it runs during the month of March. And I actually wrote a story for NBC Connecticut's website soliciting new volunteers, and I believe Connecticut had a large number of new volunteers that came online back in March. And I also included an example of how it's important, but this is just another one. I mean, rainfall and snowfall, weather is just so so localized. You can never have enough. So yeah, I mean, it's kind of tough for me to advocate for CoCoRAHS when I don't even participate in my own backyard. But you know, I do have a Davis weather station that measures rain. Maybe one day I'll have my own rain gauge, because as you probably know, they don't accept automated instruments. So
Yeah.
that's what I have to say about CoCoRAHS.
Huh. Yeah, you know, CoCoRAHS is just literally like 100 feet from their headquarters, is 100 feet from my building.
Oh,
And
so it's like
that,
close to your heart. That's why you chose this tweet.
and you know, CoCoRAHS is great, just in general. I mean,
No, it
it's
absolutely is.
yeah. I hear stories of people that have collected for 15 years or something like that, and that kind of stuff blows my mind. People who have done that every every day, 8 o'clock in the morning or whatever time it is.
Well, it's probably the modern day co-op observer.
Oh yeah, for sure. Yeah, and it's to me, the thing I like about them the most is some of their snow stuff, because with rain, generally you can get a good idea with radar. It's not perfect, but you can get a good idea. But with snow, that's a little tougher. You really rely on ground reports for that. So.
Yeah. Our next tweet is from Brian Kahn. He is a Climate Central / Weather Shift senior writer, and he dreams of skiing year round. He's on Twitter at BLKahn. That's KAHN. His tweet is, in response to Ed Hawkins' temp spiral, IPCC science chair says substantial improvement in our reports on the way.
Yeah, so this one kind of struck a chord with me. It's in a response. The article is in response to a GIF that was made that showed average temperature, and it was one of the coolest GIFs of temperature I've ever seen, or one of the coolest graphics, I guess, that I've ever seen of temperature. And surrounding it was each month, and then every year it would go every year and show the temperature changing month to month, year to year, in a circle, and the low temperatures were in the middle, and then you could see it kind of expanding outwards, showing that our climate is warming. And so the IPCC responded with, we need to make stuff like this so that people can see our message kind of readily, and they don't have to be bogged down by hundreds of pages in a report. And they're right. They didn't come off in the best way. They kind of made it sound like the public was stupid and they can't read our reports. So the way they handled it might not have been great, but they are kind of acknowledging that they need to make better. They need to put a better effort towards communication besides just the report. So I don't know if you have any thoughts about this, Tyler.
I hadn't seen that GIF before tonight. I really like it.
Oh man, it is beautiful. I'm jealous of the person who made it. What a great idea, and it went viral essentially.
Yeah, it looks like over 9,000 retweets, close to 10,000.
Yeah, so hopefully climate scientists make more stuff like that, or policy outside companies. I guess the scientists don't have that much time to spend on how their message is being communicated, unfortunately, to the public. They're working to get funded essentially, and working for science, not how the community gets their message. So we can move on to our next tweet, and this is my favorite tweet this week. It's from good friend Kelton Halpert, and it started a firestorm of tweets in the weather community. And his tweet was, "Let's make #HowToStartAMetFight a thing." And essentially what he was doing was rallying the troops to use this hashtag to make up a comment that would get meteorologists disagreeing, which isn't that hard, because I don't know, if you spend some time on Twitter, there are people arguing about stuff all the time. So I wanted to share a few of my favorites. Tyler, I don't know if you have any favorites from this.
Is he the one that started it?
Oh yeah, this was the first tweet that was sent out.
Wow.
And,
I saw a few tweets and I was very confused. I was like, what is this?
oh my gosh, JP just commented, "Weather junkies are weather brains. Hashtag how to start a Met fight." That's pretty good.
I'm actually just looking in TweetDeck now.
Yeah, you didn't participate at all, I assume?
No, I didn't participate. I don't know. I try to stay out of the fads.
Oh, come on. It was hilarious.
Oh, I know it was hilarious. It was a brilliant idea, but I caught on so late I would have looked like a fool.
Okay. Well, okay, so I had a few favorites. I actually tweeted a few. The one I tweeted that I think was my best was climate change, period, how to start a Met fight. Because whenever there's climate change in the discussion, there's always fights.
I see one here from Nate Johnson. It says warmer air holds more water. You know, that it's a little more complex than that, but so many weather communicators use that simple line.
Yeah, you know, that
it has to deal with rates of evaporation and condensation. Not quite fit for a 3-minute weathercast.
That's kind of like a blanket in terms of a cloud.
Yeah, just like the. Sometimes I feel like we're a little disconnected from the reality, and that is what people can understand in simplicity. I don't know.
Yeah,
I value the science. Obviously, I'm proud to come from a school that is all about the science, but sometimes we're a little. I think we get a little caught up in the science. Example one being hurricane warnings and Hurricane Sandy.
Well, let's not open that can of worms.
Go back to the tweets.
Yeah. So I wanted to share a few more of my favorites. Matt Lanza, but my phone app has 36% chance of rain at 2 p.m.
Oh my gosh!
Hashtag how to start a Met fight. Let's see, Fortran from Matt Mahalik. How to start a Met fight.
Kate Bilo at CBS in Philly says the NAM has been pretty good so far this winter.
Peter Mullenix, sorry, but I believe what is falling from the sky is grapple, not sleet or hail. How to start a Met fight. I'm definitely an abuser of that. I get very technical when it comes to that. And when I was teaching a class, I taught my students if it's in the winter and it's cold outside and there's pellets falling from the sky, it most likely is not hail. So be the smart one of your friend group and not call it hail.
Someone tweeted bringing up any of these graphics, and he has a collage of 4 graphics, all of them being a forecast of tornado intensity.
Oh dear. This one's from Ryan Brenton, good friend of ours. We are Penn State chants in the middle of the Oklahoma University party at the AMS annual meeting. Hashtag how to start a Met fight. I swear that happens every year, and I don't condone it. I kind of stay out of it because who cares about that during the OU party? But
I've only been to one. I can't say I remember a We Are chant, but I hope. It sounds like they go on all the time.
Yeah, they do. They do. From Todd Y, the broadcast Met. Why don't they name tornadoes? How to start a Met fight?
Oh my gosh.
Yeah. And then I think my favorite of the night, and we can end with this, is from Patrick Marsh. He was on the show previously, and all it says is begins tweeting how to start a Met fight. That kind of sums it up right there. That sums up the whole thing.
Susie Voss, a meteorologist in the Chicago area, says, I fought through 4 years of math and physics for my Met degree, yet anyone can call themselves a Met on TV. Hashtag how to start a Met fight.
Yeah, that I see conversations like that all the time about credentials and that kind of stuff. Yeah, I don't know about.
A lot of good analogies there. It's like a nurse at the hospital enjoys what the doctor does, so the nurse decides to be a doctor. I mean, it just doesn't happen overnight.
Yeah.
Anyways,
So-
I mean, that's amazing how it just takes off. You come up with a great idea and it blows up on Twitter.
Oh my gosh,
So-
it was like one of the top trending things. I guess that shows you how many meteorology people are on Twitter.
We love the platform because of how it works.
Yeah,
It's kind of like how ants flock to sugar.
I told Kelton he can stop he can quit school because he's peaked. He kind of reached his all-time peak on Twitter, I think, and starting a viral hashtag.
We have a big show tonight, though, beyond these tweets.
Yeah, so tonight we have on Dr. Matt Kumjian from Penn State Meteorology, and it's actually a pre-recorded segment. Tyler and I met up with him earlier this week. So I don't know if Tyler, do you want to give any follow-up, or should we just go straight into it?
Well, we can introduce it. Obviously, severe season is upon us. Hasn't been the biggest severe season, but a number of things interest both of us when it comes to weather radar. Weather radar is one of our greatest tools, and it's received a lot of upgrades over the last couple of years, namely dual polarization. And Matt Kumjian is at the forefront of dual polarization and Doppler radar research here in the United States. Proud to have him at Penn State, and very excited to hear what he has to say. So we'll roll the interview, and then if there are any questions from social media, we'll follow it up and end the show live. So we will return after the interview.
And we'd like to welcome to the show Dr. Matt Kumjian. He's a faculty member at Pennsylvania State University. He got his PhD, master's, and bachelor's all at the University of Oklahoma in meteorology. And right now there's a lot of research in radar meteorology, in winter storms, convective systems, and kind of the gamut when it comes to radar. So Matt, welcome to the show.
Thank you very much. Good to be here.
So I guess off the bat, I was hoping you could give us kind of the very general broad stroke of what kind of research you do right now.
Sure. So I use polarimetric radar as a tool to study precipitation physics in a variety of different storms, kind of like you mentioned. And the ultimate goal is if we can better understand precipitation in these storms and the different physical processes associated with it, then we can hopefully one day improve how those processes are treated in the weather models that we use to do forecasting.
Gotcha. So I saw a YouTube video of you being interviewed by, I think it was Ben Reppert, good friend Bren, and you were talking about kind of how you got into this field, and it was Hurricane Andrew, is that right?
Yeah, that's right. I've always kind of had an interest in storms and the sky. I wanted to be an astronomer when I was really young. And my family moved down to the Virginia Beach area in 1992. And that same summer was Hurricane Andrew in Florida. And I just remember watching the TV and kind of being fascinated by the atmosphere, being able to do something that powerful. And so from that point on, I've been hooked on storms and precipitation and weather in general.
Yeah, I think that's kind of a common theme we found in weather people, is that it's usually an event that kind of sets it off. And yeah, that's quite the event. Hurricane Andrew, that's kind of like the landmark hurricane in our field.
So I have a question for you, and it's severe weather season and prime time to talk about this. The tornado debris signature on radar, something fairly new last couple of years, and it's being used operationally now by the National Weather Service. Have you done any of the research as it relates to the tornado debris signature? And is there anything that may be cool or neat that we don't know that you could add to the discussion about the TDS?
So sure, I guess to go back about a decade now, the first paper was published by my thesis advisor, Alexander Ryzhkov, at the National Severe Storms Laboratory back in 2005. And so he had discovered the signature and analyzed it for about 3 different storms. And then in 2008, we wrote a paper together and we looked at it in a larger number of storms. I think it was something like 10 or 15. And basically found it in tornadoes of all strengths, so from EF0 all the way up through EF5. And then some subsequent work that I did in collaboration with David Bodine, who's now at NCAR, and some work by other authors, including Matthew Vandenbroeke, have really looked at a lot more statistics of this type of signature to see if there's any extra information that we can get out of it, in addition to, yes, there's a tornado that's occurring presently. And so one of the interesting things is we tend to see there's a bit of a correlation between how high that signature extends into the atmosphere and the strength of the tornado kind of in real time. It's not a perfect relationship by any means. There's definitely some exceptions that we found, but there does seem to be a general trend where if you have a taller debris signature, if it's seen at higher and higher scans that the radar does, then it may mean that that tornado is more intense. And there's also some interesting, maybe a little more esoteric things about the signature that we're noticing in some of the other polarimetric fields that indicate that there's some interesting scattering going on and perhaps some sort of preferential alignment of debris elements. But I think there's some folks doing some work on that with large eddy simulation models at the moment. But yeah, so it's nice to see this research operations happen so quickly. Now pretty much everybody is aware of this, the signature, and it really helps the forecasters pinpoint that location of where there's a damaging tornado occurring. But that being said, some of the more recent research and climatologies of this signature has indicated that only a fraction of tornadoes are actually feature this signature, and it may be because the tornadoes are short-lived in between scans, or they're far from the radar, and so the debris doesn't get lofted high enough, et cetera. There's several different caveats with that, and so it's actually much less than about a third of the tornadoes are actually associated with an observable debris signature, according to some of the work by Matthew Vandenbroeke in the last couple of years.
And for those that may not be very familiar with the debris signature, basically it's when radar can sense that it's not seeing just rain, it's seeing a mix of rain and maybe sticks or shingles or pieces of a house, and the only way that debris can get thousands of feet in the air is from a tornado, and that's how we're able to confirm that a tornado has touched down. Obviously, the hope is that the warning is out before you see a tornado debris signature.
Right.
But so the research that has made some news recently, as you mentioned, was the intensity part of the debris signature, and it's not definitive, but you know, differentiating between, say, a weak tornado and a violent tornado would be possible from this recent research. It may be tough, say, between EF2 and EF3, but you'd probably be able to differentiate between weak and really strong.
Yeah, I think it's safe to say that's plausible. Again, all the caveats associated with being able to have good distance from the radar, good coverage in the vertical dimension, and things like that. But when taken with the other traditional radar presentations of strong tornadoes and violent tornadoes associated, say, with the supercell and hook echo and a very strong Doppler vortex signature, that's always a key first thing that we need to look at. But typically, yeah, we do tend to see that the debris is lofted many tens of thousands of feet in the air for the really violent tornadoes.
The interesting thing, I think, for us in New England is that we actually see a higher rate of tornado debris signatures than places in the Midwest, simply because of the amount of forest we have up here. Have you noticed that?
Yeah, so I think Matthew Vandenbroeke's paper goes into a little bit of that. He was looking at different types of basically surface land cover, and did speculate that because of some of the areas that are more heavily forested, it's a lot more debris that's easier to be lofted. So whereas if you may have a kind of weaker tornado out in the plains, there may not be much out there in the grasslands or in the dirt for it to pick up and be sensed by the radar. Whereas if you've got trees, and especially in the fall when you've got a lot of loose leaves or leaves on the ground, it can get very easily picked up. It's a much higher likelihood that you'll be able to see that with the radar.
It's interesting because I think a first impression may be, oh yeah, this would be a great tool for Tornado Alley, but I think it really has some exceptional benefits here for us. We don't get a lot of tornadoes, but I can think of a couple of examples here in the last couple of years. There was a tornado in Worcester, Massachusetts, and there was one in Revere. I'm assuming both of those you couldn't see them if you looked out your window, but they were certainly on radar and they certainly had a debris signature. So that's just invaluable, especially in this part of the country. It's not your typical tornado that you can see, but we can get the debris signature. So at least here in the last couple of years, it has been such a help.
Absolutely, and even more important, I think, in the Northeast is that a lot of times you don't get the sort of classic big supercell storms that you tend to get out in the plains when you have big tornado outbreaks, and those are even more difficult to sort of anticipate when a tornado is forming from an operational perspective. And so some of these non-supercell types of storms, any type of information you can get from the polarimetric radars is definitely invaluable, like you said.
So I wanted to shift for a second here. We can come back to severe weather if we want to, but I was going through some of your publications and noticed you had quite a few. At least I saw 2 Colorado winter storm papers. One on thunder snow, which I did not expect to see that there because I didn't know it was that researched of a topic. And so I was curious. It seemed like it was hard to kind of classify a storm or an area of a storm in a snowstorm that was going to produce thunder or lightning, I guess. What was your kind of takeaway from that research?
Yeah, no, that's right. So we looked at just one winter season worth of data from when I was out working at NCAR, and we focused a lot on what we call these convective storms. And so these are basically very similar to a warm season thunderstorm that you might expect to see. It just happens in the winter, and so the entire atmosphere is below 0 degrees Celsius or below 32 degrees Fahrenheit. And so all the precipitation that gets formed that falls to the ground will fall as snow and graupel. And so when you look at these storms, they tend to have a cellular or kind of small isolated appearance on radar. They have high reflectivity, which indicates that it's scattering lots of energy back and you've got big particles present. But the differences between those convective cells that produced lightning and those that did not was very difficult to determine. There was a slight hint that the cells that produced lightning had a little bit more of pristine ice, and so those are talking your individual ice crystals in them that we can see with the radar, in addition to graupel, than the ones that did not. And the ones that produced lightning also tended to have slightly higher reflectivities. But it was very, very difficult. Looking at one storm, it'd be really tough to say if that one would produce or not. That being said, we did see a couple of cases of an interesting type of flash that we believe was triggered by man-made objects on the ground. So a lot of times in winter storms, your charging regions tend to take on very flat, uniform in the horizontal kind of smooth layered appearances. And if you have something like a big communications tower or a wind turbine that sort of sticks up and then provides a pointy object sticking up into that electric field, it can actually cause a discharge and can trigger a lightning strike. And so we did see that, and a few other authors have seen that in various other parts of the country. And leading up to those types of discharges, sometimes you can see this signature with the radars where the electric field is so strong that the little ice crystals in the storm actually start to align themselves so that they're not just sort of floating as they would normally would with their maximum dimension in the horizontal plane. Instead, they sort of align themselves at some angle that's it's associated with the electric field vector dimension at that, or vector direction at that point. And when that happens, the radar signal is said to be depolarized. And that's kind of a fancy word for saying that it sort of breaks. It's no longer a pure polarimetric signal that we want. And so what happens is you get an artifact in the data. If you look at some of the fields, you'll see these kind of streaks that look really fake. And when you see that, it indicates that you've got a strong electric field. And so in a couple of cases, we've seen that signature appear prior to one of these triggered lightning strikes. Now that being said, we've also seen those streaks happen when there is no lightning. So it's definitely not a pure indicator that there's going to be lightning. It just does tell you that the storm has gained quite a bit of charging and has a strong electric field.
So you guys were using a special radar for that work, that you were using chill, correct?
So in one of them, we were using the Thunder Snow paper was actually just using the operational WSR 88D
Okay.
radars. But yeah, for some of the other studies, we used CSU's chill radar and then NCAR's expand polarimetric radar as well.
So I was curious, how like what is the difficulty of real-time diagnosing an area where there could be thunder snow? Is that something that I don't know, National Weather Service might be doing, or just researchers in general might be doing?
It's such a kind of a rare phenomenon, or at least previous studies have indicated it's a rare phenomenon that it's maybe not something that people think of too often. But in this study, when we just looked at the one season, it happened surprisingly frequently. And so we're actually this summer, I think, going to be working on some proposal to potentially study this in the larger region across the U.S. Using the Weather Service radars and different lightning detection networks. Just to see really how good a job we can do in a real-time environment. When doing the study, we obviously have the luxury of going back through and taking all the time in the world to analyze the radar data.
Yeah.
And so I think it could probably be pretty difficult in real time, with the exception of these streaks that may at least tell forecasters that yes, there's strong electrification, and so it's possible that you can get a flash.
So in the other study where you did use chill, you were looking. It seemed like you were looking for these areas where there was kind of rapid dendrite collection, and I'm assuming that you were looking for areas that were heavy snow was developing. What's been the application of that research? Has it gone into models at all, like the physics of it?
That's a great question. So the application from an operational perspective is that these signatures are definitely related to increased snowfall rates, and then if you happen to have warm air near the surface, then increased rainfall as well. And so we've seen that across the country, and so we know that that's a fairly robust observation. As far as how it's treated in the models, actually a lot of the models that are used right now for weather forecasting have simplified parameterizations for these microphysical processes. So these processes like snow growth and aggregation. Mm-hmm. And so a lot of them don't really specifically account for different types of crystal habits like dendrites and plates and needles and columns and things like that. And so a lot of times you get either one sort of parameter for the aggregation efficiency, or for the growth rates of these snow crystals. There are some people doing work that's happening right now, including in our department. Professor Jerry Harrington has got a nice model that actually explicitly predicts the shapes of the particles. And so one of the things that we're going to be working on together in the near future is aggregation and how we can parameterize these processes to account for these different types of habits and these different growth regions in forecasting models.
Well, please continue doing that, because I've been living out here for a year and a half now, and oh my gosh, the forecasting is terrible for some of these snowstorms. Compared to what I'm used to, yeah, sometimes I'm like, oh my gosh, earlier this year there was a 2-inch forecast for kind of a large area. And, that area ended up with over 20 inches of snow. Wow. And it was just a day out. So I don't know how much your research can change that, but all of it helps, because it's all part of a big picture.
Oh yeah, absolutely. And these forecasts are extremely difficult. We've been looking at some nor'easters up in here in the Northeast U.S., and you see the same type of thing. When the forecast models give you guidance on the precipitation amount, it's typically given in a liquid equivalent. So how much would it be if you melted down all that snow? How many inches of rain would you have? And then so the trick then is to say, well, based on that liquid equivalent, how much actual snowfall accumulation will you get? And that is a really difficult question. A lot of times people are using a simple 10-to-1 rule, which originated in the 1800s, and no one exactly knows why or where that came from. There are some a little bit more sophisticated versions now that are based on temperature. But one of the things we're seeing with the radar is it depends not only on the temperature, but on the supersaturation, which is basically how high above 100% is your relative humidity with respect to ice. And we can see in the radar data sometimes that you've got this area of vertical motion, sort of synoptic scale or mesoscale ascent. And when that lines up just right with certain temperature regions for certain types of growth, you get very different what's called snow to liquid ratios or snow to liquid equivalents than you do in other times. And so just one simple metric like temperature isn't really sufficient for trying to capture that detail. So we're working on trying to actually measure with high resolution at the surface the snow to liquid equivalents, and then see if we can get information from the radar to tell us more about how much snow is actually falling.
So you go back to as recently as the early 90s, and we didn't have Doppler technology deployed on an operational basis. Now, 20 years later, we have that, and we have more. We have dual pole. You just talked about some research that you're working on. Where do you see the future of radar meteorology going forward? We already know so much more than we probably believed we'd ever know. Where do we go from here?
Exactly, and that's what makes it exciting. It's exciting for me just because we still seem like we're scratching the surface with this dual pole stuff, and who knows what's in the future for that. But as far as the technologies, there's a couple of different things that are starting to come in the research world right now that might be something that's happening here in the near future. The first that I think has been given a lot of attention, especially in the severe storms community, is what's called the phased array radar. And the idea behind this is, instead of having a big parabolic dish that sits and spins around and collects data, that you can actually use electronics in the array and at the antenna itself to direct the beam. And so you can do much faster updates with that. And one of the downsides, of course, is it's really expensive. But there's some talk about potentially replacing the network of radars sometime in the future, which could be decades away. Another thing we're seeing in research now is the increasing use of higher frequency radars, and especially using multiple frequencies at the same time. And so the Weather Service radars, they operate at what's a frequency band called S-band. So the wave that they send out has a wavelength of about 10 or 11 centimeters. And some of these higher frequency radars are going to be more sensitive to cloud particles and things like that. And so by combining the different frequencies together, a given particle, say like a raindrop or a snowflake, will behave differently. It will scatter that energy differently depending on what the wavelength or depending on what the frequency is. And so by comparing those two together, we can get some independent information about what's actually out there. And so I think the blending of multiple frequencies, multiple polarizations, and then more sophisticated treatments of the Doppler technology are kind of at the forefront of what we're seeing in the research community right now.
My understanding of the phased array radar is that you can scan a certain chunk of land, and it doesn't have to be a full circle like we have now.
Right, yeah, so one panel of a phased array radar, if it's a flat panel like the one that's in Norman right now, that can scan in a 90-degree sector or 90-degree wedge of the atmosphere without moving at all. And so if you wanted to scan all 360 degrees in a circle, you need about 4 of those panels. People are working on some different designs that have like cylindrical arrays or different shaped arrays that sort of increase the coverage area a little bit more. But yeah, currently the radars are sort of meant to sit and spin around in a circle. And so if you have just one storm out there, then you have to wait for the radar to spin all the way around and return to that storm. And so being able to just hone in and focus on that one storm with this increased flexibility that you get with the phased array radars could definitely help increase the rate at which you get updates of your data.
Is there any way that you could quantify the difference in price between the current radar when they were installed in the phased array? Is it substantially different?
Yes, it is substantially different. I don't know the exact numbers off the top of my head. But one of the advantages of the phased array radar, even though it's much more expensive, it's sort of thought of it more as an investment, right? So each panel of the array will have hundreds or maybe thousands of individual little transmitter and receiver elements. And so the beauty is that if one of them or 2 of them, 10 of them or 20 of them fail, that's okay. The radar still operates with very little degradation, and so you can go in and pop in new ones without much trouble. Whereas right now with a mechanical dish that spins around, if you say bust your rotary joints or the bearings wear out, then the whole radar comes down and you have to reinstall it. And so, yeah, so it's the upkeep is actually what's supposed to eventually save money in the long run. It's going to cost less for maintenance in the long run, and that's sort of the budget claim. But yeah, if you just compare, like if you wanted to buy a brand new mechanical dish and then a phased array, I would venture a wild guess that it's at least an order of magnitude more expensive for the phased array.
Yeah, that's a strong argument. And oftentimes I'll think about all these things we spend money on as a government, and then you think of a Doppler radar and how much valuable information it gives us and the lives that it can save. I mean, it's invaluable. So I suspect if we're able to put together a well-reasoned proposal for these new radars, hopefully we can get some funding for them a few decades down the road. I think I saw that the expected life for the radars now has probably been bumped into the 2030s.
Yeah, that's probably sounds about right. I mean, there's going to be maintenance and upkeep with them. I mean, these are things that are built essentially in the late 1980s and early 1990s. But yeah, no, I would agree. He should run for Congress.
And a quick follow-up to your different frequency statement there. Isn't it part of the wavelength or part of the benefit of the WSR 88D is that the wavelength allows the radar to penetrate large thunderstorms and not lose strength beyond the thunderstorm?
Yes, yeah, that's correct. So these lower frequency or longer wavelength radars, like the Weather Service ones now, they don't suffer from attenuation as much as the higher frequencies do. So attenuation, you can think of it as being kind of proportional to the frequency. So the higher the frequency or the shorter the wavelength, the more power it's going to lose as that wave is propagating through heavy precipitation. So very clearly, yeah, if you're looking at the really high frequency radar, and you'd want to study clouds, so you wouldn't be able to apply that to a thunderstorm. If you took like a W-band radar or something like that, you might be able to see a kilometer or so into a heavy thunderstorm, but then the signal would go extinct shortly after that. So it kind of depends on what type of storm and what type of processes you're interested in looking at. But yeah, definitely blending the two and sort of optimizing based on what you are most interested in. There's some decisions to be made there for sure.
So we ask everyone who comes on this show this last question here, and you already gave Tyler some good advice. Tyler Jankowski, 2020 for Congress.
Absolutely.
I like that. But we were wondering what kind of advice you'd give to up-and-coming meteorologists, and what has been the most important skill of yours throughout your career?
Wow, that is a great question. I think for the up and coming meteorologists and the students that are starting to study in the field right now, I think an important piece of advice that I could give is just to immerse yourself so much and see all the different types of activities that are going on. The traditional routes that everyone sort of just, I think, has the idea of when they come into school. I mean, that's still definitely there, but there's so much more now with all the technology and all the private companies that have sprung up, and using big data and your skills that you develop as a meteorologist when you're going through all those courses. They open up a lot of doors, not just the traditional ones that the people may think of. So definitely kind of put your ears to the ground and talk to professionals in the field, talk to your faculty in your departments, and just kind of be aware of how huge the field of meteorology is and how many different opportunities that you may not have even thought of there may be. And then for me, one of the most important pieces of advice from my career, I guess I was asked a similar question at one of the AMS meetings at a student panel. Yeah. And I think I responded something like, basically learn to grow a thick skin a little bit, especially in a career like mine where you're doing research. And part of the research process is you have to submit your papers and your proposals to peer review, and it's anonymous reviewers, and sometimes they come back with pretty nasty comments. And the idea is that everyone is trying to fight for the science to prevail. And so when the reviewer gets a paper, their job is to basically tear it apart and find any flaws and point them out. And so you get a lot of criticism. And so being able to deal with that criticism, as long as it's constructive, and incorporate that and sort of brush off any of the feelings of indignation that you may have when someone criticizes your work, and really realize that when you have someone giving you constructive criticism, oftentimes it makes your finished product, whether it be a paper or a study or something, it makes it better in the long run, makes it a stronger contribution. And so just being able to deal with that criticism and the fact that you will be hammered on reviews and you will fail at trying to get proposals funded or studies published, it's just part of the job. And so you just have to learn from that and keep going.
I love that because, we talked to a lot of broadcast meteorologists, and they definitely have to deal with the thick skin thing because they and National Weather Service the same. And I've commented how I feel lucky that my work is not broadcasted to the public and they don't find every single coding error. I'm offended yet, so
yeah, exactly.
When that happens, I'm sure I'll have to have some thick skin. So thanks for that advice. We appreciate it.
Yeah.
And thanks for coming on. We really appreciate talking with you, and hopefully we can have you on sometime soon.
Anytime, I'd be happy to. This was fun.
All right, thanks, Matt.
Thanks.
Yeah, thank you.
And that was Matt Kumjian, a professor at Penn State, one of the country's leading radar researchers. Very exciting to have him on our show, and we hope you enjoyed his interview.
Yeah, I think radar meteorology is one of the coolest research topics right now, just because it's such a visual kind of thing. It's always looking at visuals and analyzing visuals.
It's visual, and so much of it is definitive. I mean, you think of weather, and so much we don't know, and it's like 95%, but you have a TDS, you have a hail spike, you have rotation. I mean, that is actually occurring when you see it.
Yeah.
I mean, you don't have to guess a lot of the time.
Yeah, so it was really great to hear about his research and what he thinks some of the future research that's going to... I mean, radar's pretty much changed how we forecast during storms and snowstorms. So, yeah, it was great to hear what he thinks about the future of radar and if we're going to have any types of those changing moments like TDS and velocity. So I wanted to talk for a second here. We're about to end, but I wanted to talk about a second here some developments that we have going on.
Breaking news.
Yeah, breaking news live from CNN here. We're working on a website, and that'll host the show, and you'll be able to listen to it there. So look for that in the future. Tyler is hard at work. Perfecting the visuals and.
Are we not announcing the URL yet?
No.
Okay, so it's under wraps.
It's under wraps. You could probably guess what the URL is going to be, but yeah, just in case someone is evil and wants to steal it from us.
Dakota doesn't quite approve of my work, so that means I have to work harder before we can announce the URL.
Yeah, I'm a tough boss. You gotta stay in line. And another thing I'm working on, Tyler is not as involved with this. But I'm actually working on a different type of podcast that has to do with weather, completely different from the Weather Junkies. But I'll probably post it in the RSS feed, so it'll be on iTunes under the Weather Junkies. But basically, I'm looking at extreme weather events and getting the perception of the public before and after, and trying to see what weather information they were using and if it could have been better. And if they could have been better prepared for it. And so my first case study I'm doing is the Washington, D.C. supercell that happened last Monday. And I've talked to a handful of people already who went through it, and a lot of interesting stuff. So look for that. Can't wait to share that with you. Tyler, I think that's all we have for today. Is that right?
It is all we have. We do have a guest next week lined up. His name is Matt Bolton. He is a student and the lead intern for How the Weather Works. So he will be our guest next Thursday evening, and we will be live at 8 p.m. as always. We hope you'll join us then.
Yeah, so one last thing, Tyler. Sorry, I think you might have been trying to end it there.
No, I wasn't.
Okay. One last thing. Just my usual wrap-up. If you don't follow us already, you can follow us on Twitter at the WX Junkies. We're also on Facebook. You can listen to this podcast on SoundCloud, YouTube, iTunes, and Stitcher. If you're on iTunes, go ahead and give us a rating or a review. Whether it's good or bad, we just want to hear from you.
For Matt, Dakota, and myself, thanks for listening. And again, we'll be back next Thursday at 8. We hope you will join us right back here on Thursday.